I will introduce you. This is the hacker that gave the speech in the morning, and he's still alive. So I hope he's going to surprise us with his presentation. I saw the presentation. It's a bunch of pie charts. However, on one sunny day, he turned on his computer and found online on the internet 10,000 devices that were exposed, the IoT devices. And he worked together with the CERT community in order to tackle this. And he also came up with an ideas how to measure the impact of the reflected distributed denial of service. With this, please welcome Eireann.
Thank you. For those of you who saw my presentation earlier, you'll notice that I was uncomfortable talking about law the entire time. So hopefully this time we're going to do more maths and a little bit more technical detail and not so much talking about legal stuff. So essentially, after I was a penetration tester and doing hacking for 3.5 years, I went to Cambridge University's Center for Risk Studies. And they asked me a bunch of difficult questions that I couldn't answer. And one of them was, what is the maximum possible DDoS that could occur? And I realized I couldn't answer that question. It's not easy. But it kept scratching away at the back of my brain. Like, could you estimate this in any possible way? And I'm lucky enough to be friends with another guy called Eireann, and oddly another woman called Eireann. So there's 3 Eireanns that hang out together doing hacking stuff. And Eireann Kaplan is particularly good at networks and throughput and all sorts of other calculations. So we worked on this together, and we took our data from 2 other places. So essentially, after 2.5 years of scratching my brain going, how could you possibly estimate max DDoS, I thought, well, application DDoS, I don't think I can do that. Reflected DDoS, we might be able to do that. So that's what this is about. So for 2016, we came up with this number, 108 terabits a second, 108.5, if you like, terabits a second. Now, I'm not going to claim that this number is absolutely correct. What I want to do is convince you through this presentation that it is possible and that this is a rough estimate, and you might be able to do better if you use better data or you challenge some of the assumptions of the methodology. But my argument is, at the edge of a network, with reflectors and amplification factors and taking into account throughput, this is how much potential there was in 2016. So in 2017, now, obviously, I'm going to redo these calculations and see if it's gone up. And this is a yearly average, and I'll go into detail about where all those averages come from. So what I'd like to do in the future is track this over time and see if it's getting better, if it's getting worse, what we can do about it, which countries are contributing the most, which countries are contributing the least, who's been the best improver this year. You get the idea. So 108 terabits a second. What's the largest DDoS attack reflected that anyone can name? Don't be afraid. Speak up. I know I'm in the Baltic states and no one likes to shout things out, but go on. 300 gigabits a second, that's definitely up there. That's one of them. In fact, I think of that as kind of second place in citations that I can reference. Yeah, the DIN DNS attack was supposedly 1.2, and there's citations for that, so I use that one as well. So those are 2 fantastically large attacks, right? But those are 1.2 gigabits per second. And I just told you that it's 108 terabits a second is the potential that's out there. Now, I'm not saying that you could see a single attack like this, and I'll describe why in a moment. I'm just saying that that's how much potential there is. So how did Eireann and I do this? First of all, you can look at these numbers as pie charts. In fact, I'll come back to how we did it towards the end of the presentation. What I want you to see here is that you've got classic 80-20 rules. This is for DNS. So we're only focused on DNS reflectors in this graph. And again, we're looking at 2016 averages. So that's an average country count multiplied by the amplification factor for DNS and then scaled back by throughput. And I'll tell you about the throughput in a minute. But just look that the US, Korea, Japan, China, Russia, Taiwan are responsible for 50% of what is out there right at the very beginning, right? Similarly, you can do this for NTP. And you see the same sorts of countries being largely responsible. Even though you might find countries in the world that have a higher reflector count for NTP, you still see that these same countries are responsible for sort of 50% of the risk. Now keep in mind, I'm not talking about DDoS events that happened here. I'm talking about the number of reflectors we have times their amplification factor, scaled back by throughput, upload and download, which I'll get into in a minute. And that's the potential that's out there. How much was actually used is completely different. So if you're looking at DDoS attack data that comes from, say, Prolexic or Akamai or Arbor Networks or whoever, then your set of attacks in 2016 that you saw comes from this set of potential. So once again, 80-20 effects, right? Completely dominated by a few countries. These countries have so much more potential to launch DDoS in terms of volume than others, right? Now, that doesn't necessarily mean that's where the attacks came from. And that's also a risk to themselves. So US traffic can affect the US, right? Estonian traffic can affect Estonia. Lithuanian traffic can affect Lithuania. So again, SNMP, I'm sorry to bore you with all the pie charts, but I just want to get through each of the protocols that we studied first, and then we'll get to the rest. So if you don't like pi, we'll be done in a moment. So SNMP, you see the same sort of effect, the same 80-20. So what have we got? We've got, what, 4 countries that make up nearly 50% of the graph. Just right there, right? And SSDP, relatively similar, except this time it's 5 countries that make up this percentage of the graph. So I guess the takeaway here is go to the US and tell them to clean up their reflectors, right? I'm sure that'll be easy. And we can do this breakdown by ASN as well. So if you happen to run an ASN and you're curious, get in touch and we'll have a look for you at how you compare. Now, I don't know about the rest of you, but I love data visualization and quantifying things. And one of the things that was being discussed by Cyber Green Project, which is where our reflector counts came from, was how important reflector counts are with this metric. And so you can see that the average counts, so average across an entire year for each country is on the left-hand side, and our score of their potential is on the bottom. So essentially what this graph tells me is that the reflector count is almost irrelevant, right? So what is important? What's the important factor here that I really, really need to focus upon in this data? And to me, I think that's the download and upload speeds, right? For a DDoS attack to happen with reflected DDoS, you might be lucky enough to fill the download pipe to the reflector with traffic. Then it hits the reflector, and then it has to go back up the upload channel to affect the victim, right? So we need to do a min function between the upload and the download. And we need data for upload and download for these different countries and for these different networks and ASNs. So for years, I didn't have any idea where I would get that data because, like many of you, I don't have a huge budget. In fact, I have a budget of 0 for this project. So I had to go looking around for who had data, and I bumped into the network nerds at MLab, Measurement Lab. And they're really wonderful people. And they have a couple billion measurements on throughput from different countries and different ASNs. And I asked them, how did you get so lucky to have all of this data? And basically, really early on in their existence, they were able to create a network bandwidth tester widget that they got included in BitTorrent and these online services and so on. So whenever you use those measurements to see how fast your connection is, you're submitting your data to MLab. And then I was able to go and use big table queries to carve out that data and calculate quartiles for every country in the world between the beginning and end of 2016, right? So from there, I used the median. Why would I use the median? Because bandwidth isn't distributed uniformly, right? It's often distributed as a nice curve like this, right? It's not uniform. It's not even a normal distribution. There's a lot of people, data centers, who have an extreme amount of bandwidth, and then you've got these people out at the edges who just have dial-up connections, right? So my point is, those dial-up connections and so on matter, right? So I wish you could hover over this and see each of these individual countries, but I'll just save you a little trouble and tell you this is the US. So, and I believe this is China. So you can see that their upload and download speeds are so much more above averages that the amount of reflector traffic that they can reflect is higher than other countries. And that's why they're that crazy outlier that make up 22% of that graph that I was showing you earlier. Okay, so what about Mirai? Well, essentially, with Mirai, we don't use a reflection factor. We just assume that it's 1 and it can fill the pipe, right? It's not necessarily true in all cases, but we have to make some assumptions to get this to some sort of an example calculation. So is anyone curious about this calculation, or is the maths going to bore you? No? You guys won't react to anything. Ladies, will you react? Will you say something? No? Try and institute some competition. No, it's not going to work. All right. All right, well, it's just some matrix calculations, right? So let's do Latvia just to give you an example. So I have these quartiles. This particular one is the median, but I have like a max, an upper quartile, a median, a lower quartile, and a minimum. And as you can imagine, the minimums are all fairly similar, but the maxes are not so much similar. Then I have a download median, right? So essentially, this is the equation I was telling you about earlier. If I take an individual protocol and I multiply the amplification factor times the download median, and then I do a minimum between this and this number, right, because I can only use so much of the pipes, then I multiply it by the average country count for 2016. Make sense? Relatively simple. So that generalized equation looks like this and is in the paper. It's not as pixelated in the paper because I do a better job of writing papers than I do of making PowerPoint slides. I also hate Microsoft PowerPoint. So, the data came from here, essentially. So average country counts come from here. And this is the measurement lab data that covers throughput. Now, you might have chosen to use capacity instead of throughput, but I wanted something that was a little bit empirical based on user experiences over time, and not necessarily capacity changes in steps over time, but throughput can be measured many more times than capacity can, in a sense, and I get a more nuanced view, which means I can have sort of a monthly view of the changing of these values. The reflector counts, sorry, not reflector counts, but amplification factors come from here. And of course, we can argue about the variability of amplification factors and so on and so forth, but one of the interesting things about doing this work is we essentially discovered that the amplification factors are almost irrelevant because the bandwidth is what matters. Most of those amplification factors are so high that the bandwidth is being used up before you necessarily hit all of the amplification. So anyways, here's this. And this is based on a bunch of the work that was done by CyberGreen, and they have a graph. They have a number of different graphing functions where you can compare different countries over time. So reflector counts is a bit of a challenge. Anybody scan the internet regularly in here? Oh, I forgot. You're not going to respond to things. I assume many of you scan the internet very frequently. And you'll have realized that if you scan today and you scan tomorrow, you get entirely different results, right? And those results could be because someone put a firewall between you and what you're scanning. So you could go from 200 to 0, right? Or you can see a steady decline, which suggests that countries like Latvia and the CERT team are calling up people saying, hey, you're running these DNS servers and they're configured improperly. Maybe you should clean them up. And that turns out to be an externality problem. It turns out to be very much like an economics problem, right? Because if you're running a DNS server that's misconfigured, it doesn't really harm you very much. You might lose a little bit of bandwidth here and there, but you probably don't even notice, right? Everything's just a bit glitchy that day. However, other people do notice when they get hit by a DDoS. So that's essentially like polluting the internet in some sense. So this is the 5 protocols summed. And this is basically what we see as the potential for traffic. So what you can take away from this, if you want something to tweet about and be proud about, is that essentially you could have caused the DIN DNS attack all on your own from Latvia. Yay, right? Exactly, yeah. At least it's not like the 200 terabits or whatever that other countries are responsible for. Okay, so given that we have this, we can do multiple countries. And we can start to talk about global trends over time, right? So this is one of the things that I found very interesting. I calculated for these different years. I have some questions about scanning and the results from the scanning because you get this wild variation in numbers from the scans. And that's why we use the average country count for the entire year because we have so much variability. So I have some questions about the quality of data, right? But the takeaway from the presentation that I want you to have is that the max is calculable in some way and turns out to be useful, either for comparing ASNs, for comparing countries, for trying to figure out how many attackers are using how much of the DDoS potential. So as booter and stressor sites, are they getting worse? Are they proliferating? Are they using the same amount of this total proportion? That's hopefully what I get you excited about. But as you can see, the total was going up, right? So that's in terabits, by the way, in case people care. So you can see that it's going up, right? There might be some data quality issues here, but you can get your reflector counts from someone other than CyberGreen. For example, I'm thinking about looking at Showdown, whether or not I can get my reflector counts from Showdown, or whether you can get them from some other scanning service, scans.io, or do them yourself if you prefer, right? And when you get those reflector counts, and then you use the equation roughly as we've described, you get these numbers, right? So then, if you normalize that by throughput, this is the crazy numbers that you see if you just multiply it by the amplification factor. And to me, that never made sense. When I started seeing those numbers, I thought, a DDoS attack just cannot be that large. There's something wrong. And so that's why we started normalizing it by the throughput per country, or per ASN, depending on what we want to look at. And then you get this much more realistic view of the situation, in my opinion, right? But the point is, you see a steady increase over time, and that's something that we can concern ourselves with for the future. This is the number that I was most interested in as I went through this. So essentially, if you're a country and you want to increase your bandwidth and you don't do anything about your reflector counts in your country, as you increase your bandwidth, you become more of a threat to the rest of the world with your DDoS attacks. Make sense? So everyone thinks of increasing bandwidth as being an incredibly helpful thing, and we worry about the sheer volume, the sheer number of IoT devices in Africa, but most African countries have megabit connections, or DSL lines, or they're running servers on their mobiles. We shouldn't really be worried about those countries just because they have a large number of reflectors. What we should be worried about is how those reflectors aggregate to cause problems. And it turns out the countries with the most bandwidth in the world are more of a threat to the ones that have less because of this. Now again, going back to the number at the very beginning of these slides, right, 108. This number, I don't think you could see a single attack this large. I don't think it's actually possible. I think it's a max flow problem across the core of the network. So if you have data about core flows, I'd really like to see it, particularly from 2016, because I think that going from this country to that country, you would have a different number than if you went from this country to that country, or from this ASN to that ASN. And of course, some ASNs implement BCP 38 and some don't. So I'd really like to get down to this kind of granular level where we can analyze this. All right, enough pie. You guys don't like psychedelic pie charts? No? At least you're willing to laugh. That's good. It's the start of a beautiful friendship. Okay, so thought experiment. What if we ignored all of this other stuff? Like, what if we just try and make the model as simple as possible? And we calculate the average country upload and the average country download for the entire globe, for 195 countries or whatever. And then we do an average country count for reflectors. And then we multiply by the number of protocols, and we don't worry about the amplification factors and all that stuff because essentially the pipes are full anyway, right? What do we get? We get this result for 2016, which is 77.37 terabits. Personally, that's off from my original estimate by a little bit more than I'm comfortable with. So I'm not so happy with this result, and I think it makes sense when you think about bandwidth being distributed like this, not just within a country, but within countries, right? So I decided that I don't like this approach, but I thought I'd try it out just to see. The other thing that I think is important is getting access to better data. So if you have better data, I'd particularly be interested to do this with you with better data for 2017. Now, what does this lead us to? It leads us to Sankey diagrams that look like this. And I decided to compare Latvia with its neighbors, because everyone loves a bit of neighborly competition, right? So here you go. You can see this should be in gigabits per second for the different countries and the different protocols, right? So you can see who contributes more to what and get a sense of what that contributes to the global total, right? So I just put targets over here as global total. And that goes back to my point about how many DDoS attacks could this be. It's not going to be a single 108 terabit a second attack, right? That would be crazy. That's basically a perfect attacker who knows where every reflector in the world is and can maximize their throughput in every pipe around the world simultaneously. But what we do know is that about 300 gigabits per second is roughly what some of the DDoS providers feel that they can handle. So what happens when you take this number and you divide it by the number of, by 300 gigabit per second that they can handle? You get sort of 360, 365 attacks that could be happening in the world at any given time of a size that the providers of DDoS protection couldn't handle, right? And I think that's interesting. Just knowing that you could have sort of, in 2016, you could have had 360 attacks at a time that were too much to handle. And that suggests a very different economics to this entire situation than is usually presented in these cases. All right, so conclusion. I think that max RDDoS is calculable. I hope I've convinced you. You might not believe my estimate. You might want to go out and do your own estimates. You might want to get better data. You might want to look at these things differently. But I think it's useful to try and estimate these things. One of the things that's worth saying here is when I was at the Center for Risk Studies, actually I still am, but I'm just not living there anymore. When I was at the Center for Risk Studies in Cambridge, these insurance people would come to me and ask me these crazy questions. And I got used to working with other experts, experts in terrorism, experts in floods, experts in interbank lending risk. And they would come to us every day and ask us a weird question at lunchtime, like, okay, what would happen if the moon disappeared? What would be the impact on the global economy? Go and calculate it in the next 15 minutes. And you think, that's impossible. And then you remember, wait, gravity, square law, the moon is this much mass, 70% water, the tides would be this high if the moon suddenly disappeared, right? And that's basically the same kind of approach here. Instead of just saying, no, it's not possible, what happens if we try? Are we right or not? Is it useful? How could we verify this? We could rank all of these countries, and then we could take the rank of countries as they contributed to actual DDoS events, and we could do a rank correlation with statistics to see if this methodology matches up with the attacks that we've seen. It's possible, and it would be interesting. So we think it varies in time. We think it varies by counts and by throughput. We think it varies by ASN contribution and country contribution. The speed of ASN's abilities to shut down DDoS attacks, or if they've already implemented BCP38, is probably more important than all the rest of this stuff. In the future, we want to track and model it like hurricanes. We know our data can be improved, and our techniques can be improved, and we'd love your help. If you're interested in the paper, you can find it on my Twitter account, or I can make sure you have a copy yourself to take away today. And hopefully, you'll join us in the future as we improve on this methodology. Any questions?
Thank you. We have 5 minutes for questions, for questioning. Any questions so far?
What's your guesstimate on like realistic maximum amount of reflective
DDoS power?
Yeah.
I've heard from, I've had some anonymous chats with some booter and stressor services, obviously not as myself, trying to get a sense of how much they think they could guarantee me. And the limit in those conversations seems to be about 15 gigabits per second. I don't know if that's true or not. I'm trying to figure it out. But you know, that's the word I hear on the street from the kind of global black market approach. So I do think that the real limit is going to be much lower. So I think of this as like an edge potential, and then a core potential would be, again, much lower. But I don't have the data to show what a core estimate would be, right? So.
You mentioned the data now. You use the data sets. What's the validity and the quality of the data sets that you used in your research?
Great question. So from the cyber green data, you see this fluctuation in counts because scanning is hard and storing data over time, the counts go wildly different. And that's why we used an average per country for 2016 instead of like the raw count, because we would just get too much variation, right? I mean, just imagine that you get rerouted and you have an asymmetric route during the middle of your scan. That massively affects 3 or 4 countries in your data coming back, right? So some of the question about reflector counts data, I'm worried about some of the quality of that data, but so far I haven't found anyone who has better quality data, if that answers your question. If you think you have better quality data about reflector counts over time, I'd love to see it. Because the big problem is most people do a scan for reflectors, and then maybe they do another scan 2 months later, and then they do one 2 years later. It's not regular, right? And of course, the more regular you make it, the more easy it is for somebody else to spoof the results and give you weird results. So it's a bit of a chicken and an egg kind of problem. But I think that our biggest data quality problem is in reflector counts. I think our throughput data from MLab is quite good. I'm quite happy with it. If you have better data, I'd like to see that too. I'm looking at buying the UCLA data and using that as well. And I'm kind of curious how wildly different do these numbers come out when you use different data sets. And I'm happy to explore that, right? So if you're interested and you have any data, let me know.
What would be your proposal as a technical solution to counter and eliminate reflected distributed denial of service attacks as such in the world?
Well, I'm sure many of you have heard of BCP 38. So I would love to see that implemented in more places. But of course, being fair to ISPs and other, other people, BCP 38 is hard to implement. It takes some effort. It doesn't always match with your business plan and blah, blah, blah. But what we'd like to see is maybe something like this being turned into an economic model that shows the benefits to society of implementing BCP 38. Because right now, if you go to a company and say implement BCP 38, it's just a cost equation. There's like sort of no benefit. It's not like government can say to them, well, it'd be worth 2 million to the Latvian economy if you were to implement this, right? So that's where we hope to go maybe in the long run. But we're still a ways off from that.
Right, and I saw in your pie chart, not in the pie chart, in the comparison between the Baltic states, Latvia was on the second position. What do we have to do in order to get to the first position?
Increase the bandwidth, I think.
Any more questions? If not, I would really like to thank you so much for the talk. And there are some sweets for you.
Thank you.
Thank you.
A pleasure.